Hello guys, now in this video we try to find out the solution set of all the numbers that satisfy Pythagoras theorem. Pythagoras theorem could be the most famous and important result in mathematics and in geometry. It says, if the sum of the squares of the two shorter sides of a triangle equals to the square of the longer side, then the angle between the two shorter sides would be a right angle, and vice versa. For example, if the two shorter sides have length 1 and 2 respectively, and the longer side has length square root 5, we have 1 square plus 2 square equals to root 5 square. So the angle between the two shorter sides would be a right angle. If the three sides have length 2, 3, and 4, since 2 square plus 3 square does not equals to 4 square, so we do not have a right angle within the triangle. The three numbers x, y, and z could both be integers. For example, 3, 4, and 5, or 5, 12, and 13. In such a case, we call the three numbers x, y, and z form a Pythagorean triple. Now, first of all, we state the result. X squared plus y squared equals to z squared. If and only if x could be written as a squared minus b squared, y could be written as 2 times a times b, and z could be written as a squared plus b squared. If x, y, and z are all real numbers, then of course a and b are real numbers. And if x, y, and z are all integers, then we can also find integers a and b, so that x squared plus y squared equal to z squared is valid. We break down the proof into two different parts. First of all, we try to prove it from right hand side to left hand side. So, we simply plug in the numbers. We put x equals to a squared minus b squared, y equals to 2 times a times b, and z equals to a squared plus b squared. And then we write down x squared plus y squared. Now, after a number of expansion and simplification, we find that it could be written as bracket a squared plus b squared close bracket all squared, which is the same as z squared. If x, y, and z are all real numbers, then of course a and b are real numbers. And if x, y, and z are all integers, then a and b could also be integers. So the proof is done. Now, and then we try to prove from left hand side to right hand side. We rewrite the left hand side as x squared equals to z squared minus y squared, which could be factorized as bracket z minus y close bracket z plus y close bracket. And then we can write z minus y equal to v squared, z plus y equals to u squared. That is to say, x squared equals to bracket v times u close bracket all squared. Or maybe x equals to v times u. Since v squared is less than v u squared, we can put v equals to a minus b, and u equals to a plus b. So, x equals to a squared minus b squared. Now, u squared equal to z plus y, which is bracket a plus b, close bracket all square. We call this equation number 1. v squared equals to z minus y. and is equal to bracket a minus b close bracket all square. We call this equation number 2. If we put equation 1 and equation 2 together and find the sum, then we have z equals to a squared plus b squared. And if we deduct equation number 2 from equation number 1 and further simplify, we have y equals to 2 times a and b. So, the proof is done. And we have the solution set. Now here are some examples. We could have x equals to 3, y equals to 4, z equals to 5. Or maybe 5, 12, and 13, 7, 24, and 25, 8, 15, and 17, 9, 40, and 41, 11, 60, and 61, and so on. And there are indeed an infinite number of Pythagorean triples.